All right, so let me talk about the Farrer expansions, which are also relevant in the construction of Lie group integrators. Okay, so again, we wish to express a solution of this model differential equation on a Lie group in the form y of t is the exponential of the integral from 0 to t of a cos c d cos c, right, times some other sort of variable. It's like v of t, it's like which again we want to live under the group, right? So we want to sort of obtain a differential equation. It's like which v satisfies, right? So of course what you can do is you can multiply on both sides by e to the minus of that integral. It's like, and then you get v of t is e to the minus of the integral times y of t, and then we differentiate that directly. Okay, so we do some direct differentiation. Okay, so what you end up getting is that v prime is equal to just the time derivative of this exponential term, well, of the minus sign. Okay, times v of t, sorry, y of t, because I've expressed v in terms of y, right, which is how I'm computing this derivative, right, y of t plus the e to the minus integral from 0 to t of a cos c d cos c, and then the derivative of y, right, so y prime. Okay, so what I'm going to do is I'm going to substitute the expression for y into this, and substitute the expression for y prime into this. Okay. And the idea is to write everything so that it's some sort of operator acting on v, which is more or less what we'd like to do. Okay. So this is equal to d dt of e to the minus integral from 0 to t of a cos c d cos c. Okay, and y is this e to the integral from 0 to t of a cos c d cos c v. All right, so I'll leave that there. And then this other term is plus e to the minus integral from 0 to t of a cos c d cos c. Y prime is this thing, right? So e to the integral from 0 to t of a cos c d cos c. And that's times v. All right. All right, so you just have stuff acting on v now. Okay, so that's sort of a good situation to be in. And then I'm going to collect all these terms together in terms of the big add operator. Okay. I'm sorry, there's an A here, right? Okay. So, all right, so what's happening, if you will, is that this is the conjugation of A by this exponential thing. So this is what I'm writing here, right? So this term corresponds to this. And then this term is given by the dx expression at the point here, the matrix exponential minus integral from 0 to t of a cos c d cos c, right, at, and the whole thing acting on v. Okay. All right, so that's a little bit complicated, But what we're going to try to do is we're going to try to interpret these things back in terms of other expressions which we saw before. It's like in defining in particular the series expansion for dx, right? So let's see what happens when you do that. Okay, so if you do that, so v of t satisfies. Oh, sorry, before I do that, I should say that these things have some nice expressions, so you can check that sort of big add with respect to an exponential of some operator applied to d is equal to the exponential of the little add operation of e. Okay, so there's some sort of relationship between the adjoint, the conjugation, and the sort of the linearization. Okay. All right. So that allows us to simplify this expression. And then the other thing you can check is that the exponential of e applied to d is equal to e to the little add e minus the identity divided by add e whole thing applied to d. So this, of course, we saw before. It's like when we were looking at the series expansion, it's like for dx, right? Okay, so in any case, with these identifications, then you can rewrite these two terms in terms of the adjoint operation with respect to this integral. Okay, so so what happens is that and of course, I guess in both of these cases, what you have, of course, is that e is actually just a of t, right? So that's what's happening here. Okay. Sorry, no, d is a of, sorry. So d is a of t, right? That's what we are applying it to, right? We're applying this add exponential or something to something. That d is a, and then e is this integral, right? So e is the integral from 0 to t of a cos c d cos c. All right, so that's the identification. It's like here, and then with that you can write that v prime is equal to the identity plus add e, okay, e to the minus add e minus the identity over add e, the whole thing applied to d, which is this a thing, and then you have v here. Okay, and you can write this a little bit more explicitly if you prefer, in terms of a series expansion. So this is sum from k equals to 1 to infinity of minus 1 to the k, k over k plus 1 factorial, and then this add operation to the kth power. It's like by the integral from 0 to t of a cos c d cos c, all right? And you apply it to a of t, and then this is times v, right? So that's the differential equation for v, and then you can sort of do sort of an iteration, right? Something like a Picard type iteration to get sort of terms. Okay, so we can iterate this with some initial iteration, which is just the A matrix. Okay, and then you get a sequence Bm of t, which is sum from k equals 1 to infinity minus 1 to the k, k over k plus 1 factorial, add k, the integral from 0 to t. Instead of the full-blown thing, it's like you just have b. I think this should be a at times 0, I guess is what you should be doing. Then bm minus 1 t. So you can construct an expansion like this, All right, and then this is what is called the Ferrer expansion. Okay. So if as you compute each of these BMs, then you can construct a better and better approximation of the solution by saying that y of t is equal to e to the integral of 0 to t b0 cos c d cos c. Actually, I should say this is just a of t, I guess. Yeah. All right, and then e to the integral from 0 to t of b1 cos c d cos c, and then you sort of keep doing this, and eventually you apply it to y0, right? And the hope is that as you sort of take the expansion out, it's like the higher and higher order terms, it's like matter less and less. Okay, so this is another way of constructing. It's like a practical sort of Lie group integrator. And again, it's like a lot of these things involve integrals. So in practice, of course, you have to do quadrature approximations of these things. Okay. So let me just stop here.